Tesla coils. There is always something mystical about them, especially when they make music. So today I'm in the quest of finding the most simple solid-state Tesla coil circuit that works. And although it seems there is a lot of complex electronics involved, I did manage to find this schematic that uses one single MOSFET and has auto-tuning feature. And spoiler alert, it is the one I played in the intro of this video. So if you want to see how I made it sing using Arduino, then this video is for you. But first of all, this episode is a special one, as at the moment of editing I did pass 1000 subscribers on my channel. So I want to thank everyone who subscribed, as this is the only thing that motivates me into making this kind of content. Although earlier I made some tests using a breadboard, now it's time to give it a proper board with fixed electronics. So I soldered all the components step by step and also made small modification that I would explain later on this video in the full schematic. One key element is this small transistor that disables the main MOSFET by putting the gate potential to the source of the MOSFET, hence disabling the oscillation at will. The brain of this operation will be this Arduino Nano, which I'm going to solder next. I've decided to use an Arduino because it is more convenient to change the functionality of this Tesla coil simply by changing the software than by installing new hardware components. Some examples of different functions would be setting the output frequency with a simple potentiometer, changing the duty cycle, and also sound modulation of the electric arc, aka music. The board I'm using has strips of conductive material which I had to remove in order to isolate some parts of the circuit. I also added this potentiometer so I can manually control the output frequency of the electric arc. I then carefully reinforced with solder all the conductive parts that carry high current. I also added these two sockets in parallel with the capacitor, just in case I need to later increase its value by adding more capacitors in parallel. Now having a quick test of the Arduino, and nothing blows up. So far so good. I also added this snubbing circuit made of a resistor and a capacitor that will protect the main MOSFET from high voltage spikes induced by the primary coil when the transistor is turned off. After some final touch-up with the soldering iron, and this is what came out. All the components fit nicely on this board. On the right side we have the main MOSFET with a heatsink, two surge protection diodes, one for the base and the other for collector of the MOSFET, the input capacitor. I have also switched the control MOSFET with this bigger one, as it works better than the one I showed you earlier. Also, the most important part is this snubber protection. Without it, the MOSFET will be toasted in no time. On the left side I have the programming unit, which is an Arduino Nano. The generated signal is later inverted by this hex inverter and then fed into the control transistor. This potentiometer is optional and I only added to manually change the frequency output. So let me explain how it works. As you can see, the only functional modification I have made to the original schematic is to add this small transistor here that when it's turned on, it forces the main MOSFET to shut down by putting its gate potential to its source, aka ground. In other words, the Tesla coil will oscillate when this small transistor is off and will shut down when the transistor is on. Hence it's a negative logic, and here is where the hex inverter comes into picture. The plan is to play some MIDI notes, and in order to create music, the Tesla coil must oscillate only for the duration of each note and to be turned off during pauses. If I remove the hex inverter, it will work exactly the opposite. Now that we have successfully finished the hardware part, it is time to plug the Arduino board and write a simple program that changes the frequency output based on the position of my potentiometer. In this example, I will start with a duty cycle of 10%, which means that 90% of the time the transistor will be turned off, hence limiting heat output. Here is how modulation works. The Tesla coil is oscillating at around 700 kHz and is always auto-tuning itself when the capacitive environment changes. If I zoom out, you can see that all that oscillation earlier happens during that 10% duty cycle and is modulated in this case at a frequency below 100 kHz. With a higher frequency, I have also managed to get some hot plasma arcs that I would not really want to touch with my bare fingers. I really wanted to play some music though, but I found out the hard way that modulating each note with a fixed frequency and time period is a painful and time-consuming process. Luckily, I did manage to find this page on GitHub that has many interesting MIDI soundtracks already coded in Arduino. Whoever did this, I give him proper credit and leave the link in the description because he truly deserves it. Now the only thing I had to do is copy the code, changing the output pin according to my setup, compile it, and you can check out the result in the following tests. Let me know in the comment how many of these sounds have you recognized. Also, if you enjoyed this video, press a like and subscribe because way cooler projects are coming. Bye bye!